Hello everybody, this is our last lecture for the electrochemistry chapter, and it is our last lecture of the entire school year. Believe it or not, you're basically done. You've come so far, you've learned a ton. I know this class is not always easy, but I hope you know that I'm really proud of the hard work you've done this year and the fact that you were brave enough to take a really hard class and you're going to go into college having learned so much chemistry, having learned to be a much better student, learning how to persevere, all those good things that don't come when you take the easy route. And AP Chem is for sure not the easy route. So I'm really proud of you. Last lecture. We get a kick out of giving it this silly title, our Variables Unite. In this lesson, you're going to see this come back to equilibrium, and we're going to come back to thermodynamics, and I love that full circle moment that we get in our very last lecture. So let's get started. You should have a glue in that looks like this, and you can see here all the different parts. We have equilibrium, we have thermodynamics, and we have our electrochem chapter. And they're all connected. You're able to go back and forth between equilibrium and thermodynamics using Gibbs, right? We see our equilibrium constant here. You're going to be able to go from equilibrium to the cell potential. And you're going to be able to go from our electrochem or cell potential to Gibbs. Let's see if it's spontaneous or not, right? You're going to have the ability to bounce between these three topics. So when we have a spontaneous reaction, remember one direction is going faster than the other. We proceed in the forward direction more than the backwards direction. Our delta G is negative. We saw in an earlier lesson that our cell potential is going to be positive. And we would see that we would be product favored. Here we can relate them together. N is going to be the number of electrons. We're used to seeing that for the number of moles, but you need to be careful here because that's the number of electrons that are involved. And then we have Faraday's constant. Don't be bothered if you see it rounded decently far. That's pretty common. Oops, let me get rid of that extra zero. Hold on. Nothing quite like typos in your last lecture, right? All right. So here we have an equation and we are wondering whether this is going to be spontaneous or not. We're going to figure out how many moles of electrons are being transferred. We have our constant. And we can plug it into the equation you saw earlier on the slide. I see here that 2 electrons are being transferred, aren't they? So 2 moles of electrons. And when you do that calculation, you find out that your delta G is negative. So if cell potential was positive, delta G is negative, this is spontaneous. We don't have to force this to happen. Here's a helpful equation called the Nernst equation that we use when we do not have standard conditions. If you remember, for our electrochem chapter, a standard condition is 1 molar concentration. And it's not very practical to assume we only ever use 1 molar concentrations. So this will allow us to convert. You'll see here Q, right? Remember that from our equilibrium chapter? And you'll notice we have the one with the not symbol and the one that doesn't. Sounds so silly to say it, but the one that does not have the not symbol. This is the standard And this is because we're not at standard, right? Some people find it helpful to see rearrangements and how we can get from one equation to the other. You remember this from thermodynamics? And what we can do is we can say like, okay, here's the new equation. And I'm replacing the delta G, aren't I? If delta G equals negative NFE, then if it's the standard condition, I put the standard version here. And if it's non-standard, you'll see we leave the not symbol off. And now we can simplify and rearrange, and this is what you end up with. It is not that they're going to ask you on the AP test, okay, rearrange and show me how you derived your equation. But if they give you certain data, you can plug and chug and rearrange a lot faster if you're comfortable with those kinds of rearrangements. We often see the equation, the Nernst equation simplified. If you're at 25 Celsius, this just saves you some time and some work. And you may see this rounded slightly differently, no big deal. So let's look at this cell real quick. Here we have concentrations that are not 1 molar. And here we have our 1 molar standard conditions, and you can see what the voltmeter reads, 1.1. But over here I have 0.01 concentration on one side, and I have 2 molar on the other side. And look what happens. I'm getting a higher voltage, aren't I? So we can play around with our concentrations to try to get conditions that we want, try to get voltages that we want, by not always being at 1 molar. Now let's connect this to equilibrium. So when we're at equilibrium, we know that the forward and backwards reactions are happening at the same rate. But if this is a battery, if that's, a battery cell that you're working on, that's not good. That means it's dead. If you're going forwards and backwards at the same rate, you're not going to have this net drive of electrons in one direction, which means your cell potential is 0. You're not able to get your current to go, to run your light bulb, or whatever it is you're trying to do. So that's not good. So one thing you could do is take your equation and say, okay, well, equilibrium constant, K means I'm at equilibrium. Q meant we weren't at equilibrium, so our battery kept working. But if you're at equilibrium and you plug in K, you're going to have 0 volts. It's dead, doesn't work anymore. So if you know your standard cell potential, you could use this to calculate K. So while a dead battery is not super helpful to us to perform our work, right? It could be helpful to help us calculate an equilibrium constant that we didn't know otherwise. So let's give that a try. We have the same equation. We know that at standard conditions it's 1.1. And because we're using K, because we're at equilibrium, it's 0 volts. If you were not at equilibrium, right, this wouldn't work. 0 is only if you're at equilibrium, if it's dead. So rearrange, solve for K, and you get your equilibrium constant. This is a slightly different type of cell than the ones we've been looking at so far. Earlier, our cells had different materials on each side, didn't they? Here we have the same substance. Do you see we have zinc 2+ on both sides, We have zinc electrodes on both sides, but the concentrations are different. So when that's the case, what we have to do first is figure out which side is going to be oxidized and which side is going to be reduced. We're going to have our 1 molar side decreasing and our 0.1 is going to increase, isn't it? So when I write my equation, in order to get this concentration lower, some of it needs to turn into neutral zinc. We got to get some ions out of that solution, which means they need to be reduced. And if we're trying to make more zinc ions over here, we got to get some of the neutral zinc to turn into the ion, which means it needs to be oxidized. So really what's going on here, right, is our 1 molar is moving towards the 0.1 molar side, or the 0.1 is getting bigger and the 1 is getting smaller. And that helps you figure out which is being reduced and which is being oxidized. So now, we are not at equilibrium, are we? So I need to put a Q. Be very careful about that. They're really picky. They want to see that you understand that K and Q are different. And this is a great place where that comes up. Okay. And we find out 0.03 volts. Okay. Remember, our electrolytic is when it's not spontaneous. That's when we have a negative cell potential or a positive Gibbs, right? We have to hook it up to an external source, an external battery. And we got to get those electrons to flow because they're not going to want to do it otherwise. We're trying to force them to go the direction we want them to go. So one of the things that will often happen is they will ask you to determine whether something is voltaic, galvanic, right? Or if it's electrolytic. In order to do that, you got to figure out the cell potential symbol or algebra symbol plus or minus. Or Gibbs, you could figure out if delta G is plus or minus. Depends on what data you have. And just a reminder from our previous lesson, right? When we have our galvanic voltaic cell, anode is minus, cathode is plus. What an ox loses, a red cat gains. But in our electrolytic cells, we're getting electrons from the anode, which is attached to that battery. Okay? And therefore the cathode is the opposite. So thinking about the electrons and where they're going can really help determine plus or minus for you. I love this picture with them side by side. You can see anode is losing the electrons and they're going towards the cathode. Here, they're leaving the anode and going towards the cathode. That's still true. It's just the plus and minus that we change. We still have a salt bridge. We still have our electrodes, right? That's all the same. We're just forcing it to go the other way. It naturally wants to go this way. We're forcing it to go the other way. One thing that comes up is electrolysis of water, because that is something that doesn't want to happen on its own, but you can use an external source right? A battery source, an electrical source to force it to happen. These equations for water are incredibly helpful. You got to memorize them. Okay, whatever it takes, just get these memorized for the for the electrolysis. The thing that's really weird here, if you notice, is that we got water on both sides, right? But some of it is gaining and some of it is losing electrons. You got to remember what's being produced. I like this picture because it's reminding you that you make your hydrogen gas and you make your oxygen gas. And then down here you can see that all you're trying to do is figure out the missing pieces to balance those equations. So if we're in an acidic solution, here's our anode, here's our cathode. We can add those together and we can see that delta E is negative. That's not good because that means delta G is positive, which means it is not spontaneous. That's why we have to force it to happen. And then last little bit here, electroplating. It's one of the big examples for this chapter, kind of real life examples. Here we have silver losing its electron, and here we have it gaining. What we're trying to do is get silver from one place to another. We're trying to plate it from one source onto some other piece of metal that we want to turn into a silver coating. So you have to have your solution be the metal that you're trying to plate. Your anode, see here is a silver bar. My anode is silver. Some object. I have no idea what they think this object is supposed to be. I don't know. But I love that it shows you all the ions. So our mystery object over here. And then because this is not going to be a spontaneous process, we need to hook it up to our current. So those cations are going to be turning into neutral metal and sticking on to the object of interest. It doesn't have to be silver. They do this with all sorts of things. And what this silver electrode over here, what our anode over here is doing, is replenishing the ions that are being plated. So as long as you have this and you keep using some of this up, you can keep plating. You're going to gain mass over here on the cathode. The red cat gains what an ox loses. So the anode is going to lose mass. And then, like I was talking about the other day, we can turn this into dimensional analysis to figure out how long it would take or how many grams you could get, things like that. So if I want 5 grams, I'm going to convert to moles. You can see here we're only dealing with 1 mole of electrons. Here we can convert from moles to our coulombs. And remember, 20 amps is the same as 20 coulombs per second. And we get our final answer. That's how long it would need to take to get 5 grams to plate out if you have it set to 20 amps. Okay? So your very last lecture, you are officially done. You got 1 more set of KCQ boxes and 1 more set of color annotations. And then we'll have lots and lots of studying before the AP test. So We're not quite done with the school year yet, but you are done learning new things, which hopefully feels really good. Hopefully you feel really accomplished and a little bit relieved to be done, okay? All right, everybody, that is it. I hope this was helpful. Bye.